Can you check that it is being recorded? Somebody confirming that it's being recorded?
Yes, doctor.
Okay, thank you. So let's go on with the example. Okay. This process, this operation could be completed. Again, you could have a complete final expression. It is very long. That's why I didn't have the time to type it. But I guess I'm not sure if in Logan's book it is presented. But it's possible, or in another book. But you can imagine that this is very long expression. You have betas and gammas and nus in there. So that's a lot, because you have two operations, two matrix operations, and you will see that in a minute. Okay, so this is the application that I'm going to show you. So let's suppose that we don't have the plate like this, we have it like this. And in this case, I have a vertical force. So we are seeing something like this. So it is plane stress case. So in this case, we have a long, like a flat bar. It's 2 meters long, because these are centimeters, 50 centimeters in height. It's a very high the section. And the thickness is 1 millimeter. 1 centimeter. Let's suppose that we apply a force 3 tons in the end. Okay, this is a plane stress problem. So let's do a discretization. 4 elements. Each one is a triangle. And as the simplest case, I'm not going to say much about that. We can say something about that in the next session. Let's take half of this and put it into here, and the rest down here. As easy as that. So let's go on. So after defining this discretization, this is the connectivity table. And we can check, for example, element 4. Element 4 goes from joint 2, 6, 3. Okay? So you go 2, 6, 3. You see? In this sense, it's counterclockwise. Okay? And that's the same for each one of these 4 elements. So let's calculate the stiffness matrix of every element. So remember that when we calculated these gammas or betas and gammas, we had differences in x's and in y's. So since element 1 and element 3, see, element 1 and element 3, they have the same dimension. In x and y, both are the same shape. So the calculation of the stiffness matrix for the 1 is the same for the 3. The same you can say for the elements 2 and 4. After calculating the stiffness matrix, and when you try to form the global, that's different. But the stiffness matrix itself is the same. So this is for element 1. So element 1, this is the same figure as before. You have here, here, and here. This from here to here, this is 200. See, from here to here, this is 200 centimeters. So this point here has an x position of 100. That's what you see here. So joint 1 is 0, 0. Joint 2 is 100 and 0. And joint 3 is 150. That's what you have here. From there, you calculate alphas, betas, and gammas. With that, and knowing that it is steel, you can take the value for nu and E. The thickness is uniform, 1, and the area, you can calculate the area here easily. Okay? So, this is the application. So this is B transpose. This is D, and this is B. So what I've done here is multiply this times that first, and then the result of that is multiplied by B transpose. There. So that's the result of multiplying D times B. Okay, this is 3 by 3, this is 3 by 6, the result is 3 by 6. This is 6 by 3, this is 3 by 6, the result is going to be 6 by 6. So that's the result. Okay, in this case, remember that in front we have this expression. Okay, so we have TE over 4A, 1 over minus nu squared. In this case, it's still, so it's going to be 2.1 times 9.8 to the 6, because this is newtons per centimeter squared. And all of that. Questions, people, so far? So remember, okay, this is multiplied by, or this contributes to the equilibrium of F1 X, F1 Y. The other is 2, so this is for F2 X, F2 Y. And the other is 3, so this is F3 X, F3 Y. And this is the vertical direction. This is U1, V1, U2, V2, U3, V3. Remember, you have to have that in your memory, in your mind, in order to form the global stiffness matrix. That's something that we have done many times. Okay? We can do the same for the other two elements. Okay? So remember, okay, elements 1 and 3 contribute with this stiffness. Element 2 and 4 are similar. They're just located in a different position. So we get this value here. So we discretized procedure, and finally we have found the stiffness matrix for every element. We assume continuity and consistency in order to produce the global stiffness matrix. So in this case, as we said before, okay, we have, these are the forces in joint 1, 2, etc. These are the displacement in joint 1, 2, etc. And in this case, this is the element 1 relating joints 1, 2, and 3. That's why this matrix, these values are replaced into here. The rest is 0. So that's the contribution of the first element. Then we go for the second element. In the case of the second element, you go 1, 3, 4. Okay? So this is 1, 3, 4. This is 1, 3, 4. So this value here adds to here. This value here adds here. And this is 1, 4. And what in this case, because I did this in Excel, what I did was I generated this stiffness matrix of element 2, but in the general, in the global sense. So I have the stiffness matrix of the first element in the global sense, because as you can see, I include the 6 joints. And here, I do the same for the element 2. So this is a 12 by 12 matrix, and the other was 12 by 12. So what I have to do is simply sum the 2. And then I can do the same for the element 3 and 4. And at the end, I just add the 4 matrices. Each one is expressed in the global sense, including all the joints. In Excel, that's easy. That's why I did it like this. And this is finally the global stiffness matrix. So we can identify then that the joint 1 cannot move. Of course, this is X direction, this is Y direction. So element joint 1 cannot move in either direction. Same for joint 4. So this is 1, this is 4. We put a large value, and on the other side, we put K, this large K value, times the value of the displacement that we want as a result. Since all of this is 0, that's why we see here, that's 0, and this is 0. If you want a different value, what you have to do is replace here this large one, in this case, 1 to the 30th, times the value of the displacement that you desire. Here, negative. So this is going to be F5Y. This is going to be F6Y. Both downwards, negative. And you're ready. You solve it. These are the displacements. These are the external forces. Of course, these are the two that we had. And you see that you have no force in the X direction. No force in the X direction. Joints 2 and 3 are completely 0 because there is nothing here. In joint 4 and 1 and 4, okay? You have the reactions. You see here that this is positive, very large, so this is negative, so it's points downward. This is strange, this. There. This is strange. I was hoping that these two will be in the opposite direction, but anyway, we'll have to check. It's possible that I made a mistake here. I have to check. Yes?
What is the reference for the force?
It's the same for everybody. See, from the beginning, it's the same. It's the same. Remember, we started saying this is XY, XY. We took these positions according to the reference system. It's one single for everybody. Remember that the forces, all what you need is the convention, sign convention, and then just go on. Did I answer your concern? I don't know who was asking me. Who was asking me, people? Did I answer or?
Yes.
Okay. Is that what you were asking for? Yeah, the reference system is fixed all the time. There's one single because all elements are located in the same plane. There's no like this. See, all flats are in the same XY plane. And then we can do the same as we did before. Okay, so we can interpret. Probably I forgot to change. I promise I'm going to change this figure for next session. So I'm going to review these numbers and this figure because probably this belongs to a different example. It's possible that this belongs to, I don't know, maybe positive values or something like that, but I'm going to change that. That is something that we're obtaining. And you can see that there is, in this case, there is equilibrium as it should be, okay? Displacements, you see that this is 2x. This point is moving in the negative x direction, so it's moving to the left. This is the sixth joint, which is this one here. You see this moves to the right and moves downward. But you see that to the right moves 2 zeros, 1 8. To downwards moves 1 0, 6. So this is basically 10 times that, much larger. So in the x direction, basically there is not much. In the y direction, there is a large deflection. That's something that we have assumed. Okay. Also, probably, you can see that if you compare between the 5 and the 6, see the 5 moves to the left. So this point moves to the left. And the 6 moves to the right. So you have vertical and you have something like that. Makes sense. But please,
Doctor.
Please, just a second. Here, you are analyzing a beam, but we are not considering the kinematic hypothesis. So this is like working in the elasticity area. When you're working in elasticity, you do not any type of assumption. When we do solid mechanics or structures, we start doing assumptions, like the kinematic assumption. In this case, there is no assumption. What we can do is we can get more elements, and from there, we could try to see if it's indeed, in this case, the kinematic hypothesis is satisfied or not. Okay, there was a question, somebody? A question, somebody, question?
Yes. Because the force 1 and 40 in up is different in down, the direction.
Yeah, but remember that you have one force here downwards and one force here downward, and also you have two forces downward here. So this plus this has to be equal to this one here, but in the opposite direction. The idea is if you consider the four forces in the upper in the vertical direction, the four have to cancel each other. That's what you need to find out. Wacon?
Yes, doctor.
Okay, so remember, it's not only 1, 2, 4, no, it's all the forces in the vertical direction, they have to cancel. Summation of forces, all forces in the vertical direction. So summation of all forces in the x direction, and they have to cancel. In this case, you have only two reactions in the x in the two joints in the x direction. So they two have to be equal to each other and in the opposite direction. And this is something that you see here. This is plus, this is negative. But I have to check because it looks like it doesn't coincide. People, I'm running out of time. You can go on. We can review this. In the last part of this presentation, okay, this is a program, okay, which is already implemented. My wife, a long time ago, when we returned from Michigan, I asked her to help me. And so she typed all of this, the instructions of this program, and we made it work. So this program is available. So I want you to use this program in order to solve this, the assignment number 4 as a group, okay? So here you have description of the variables, okay? Okay, this is the input data. Again, you have to generate a file, a text file using Notepad or anything like that. And this is the way you have to organize the material, the values inside that. And here, well, you got variables from 1 to 4, and then 5 to 7. There are some notes you have to be, for example, note 2, units must be consistent, yes. What I would say is that, where is the material properties? For example, you have E. What do you suspect this is E for? What is this variable for? People, tell me. E. E is for,
doctor.
exactly. This is Poisson ratio. Rho probably is the density. It is possible that they require this for all their calculations because we don't use rho. And this is the thickness. Okay, so the Young modulus has units of force and units of length. So that's the central point. So every force has to be using these units of forces. Anything in length has to be using these units. That's it. That's consistent because there are only two main characteristics. There are some, and here there's an example. Okay, in this case, it's a plate with two forces in the x direction. Okay, here, this is the data file. Okay, so you have 10 lines, and you can interpret what this means in terms of this. Okay, so probably here you have 1, 2, 3, 4. Probably these are the joints. So these are the position of the joints. Okay. So you see here that 0, 0, 0, 0, 10, that's joint 2. This one here is going to be 20, 0, 20, 20, 10, 20, 0, that's 3 and 4. And then you have the connectivity. Element 1 is 1, 3, 2, 1, 3, 2. Element 2 is 1, 4, 3, 1, 4, 3. So I'm going to post this program executable. You have to generate a source data file in order to make it run. Okay, so the problem that I want you to solve is this. Let me here. I hope you can see. Can you see the word? Can you see my word, people?
Yes, doctor.
Yes, doctor.
Okay, so this is the problem that I want you to solve. Okay? If I have a plate like this one here, and I apply a force in a point. Okay, people, this is not a distributed force on all the edges. No. Let's suppose we have, and you apply a force in the center of the section. What happens if I make a cut? Probably this is something that you saw, you studied this in solid mechanics. If you make a cut here and analyze the distribution of the stress, you're not going to have something like this. You are going to have something like this. If I make a cut here, I'm not going to have something like this. I'm going to have something like this. If I make a cut here, yes, the stress distribution will be very close to uniform. So if you apply this force here in a very concentrated way, the stress in this area will be much larger than just F divided by A. And what I want you to do is you calculate this stress concentration factor. And that depends on the position along the x-axis when you make the cut. So what I want you to do is to analyze half of this, because this is a symmetrical, and discretize this part using an adequate number of triangular elements, and then analyze in different cuts the stress distribution. With the stress distribution, you can calculate the concentration factor, and you can compare those results with those results available in the literature, because this is presented in many references. This has to be completed in groups. Remember, Isaac, do we have the new groups now? Are all format now? No? Genesis, do you know if we have the new groups already organized?
No, I don't know.
People, remember, in this case, I need to have at least one female and one student from outside Guayaquil in every group. We have enough of everybody, everything, enough females, enough students from outside, so everybody will be working in a different environment, working with people who probably express themselves in a different way. That's what we need you to do. Questions? Questions? I will post this in a minute. Questions about this, people? Any question? No questions. Good. In that case, that's it for today. I'll see you Monday. If I have any questions, I'll try. Send me an email, because today is going to be extremely difficult. I have to go to the campus. I have to sign something. Then I have to do something similar in downtown. Then in the afternoon, I have a meeting at 2. Then I have a class at 4:30. So today, be patient, okay? If you send me an email, try to do it after 7, because otherwise I don't have the time to answer, okay? Tomorrow it's better, but please try to start right away. The last thing to insist, I am not going to accept groups that do not satisfy the restriction that we have just explained, okay? And the most important is the reasons behind this. The reason is that you get used to work with people that you do not know. Okay, that's the reason. Okay, if there is no more questions, then I'll see you Monday. Bye-bye now.
Doctor, I have a question.
Yeah, go on.
About the program. Is the program allows decimals?
Yes, there is no problem.
Yeah. The question is because I didn't see decimals in the caption, but okay,
oh no, yeah. You can see. Yes. It's in Fortran is written in. Oh well, if somebody is interested, yeah, I can share the program, because it's not mine. And the program it was published in the appendix of Logan's book. Okay, so it's not mine. So if somebody wants it, yes, I can share it with you, the source code. But I'm in principle, I'm going to share with you the executable. So you click it on the executable and it starts running. And it will ask you for the name of the data file, then the name of the executable file. So the name of the data file is the file where you have previously prepared all the information. So you start reading, make the calculations, and put all the results in a different file. Yeah, but if you are interested, yeah, and you can see that it is, it considers real. So when you consider real, you can include or do not include decimals. In Fortran, when you define something as an integer, you cannot use dot or a point to define it, because that imply decimals. And that decimals are not adequate to be in an integer value. Yes, you can include many decimals. Well, not many, but I think in general, simply single precision variables in Fortran imply, I think it's 7 digits. Oh, I'm not saying 10 to the 7. I'm saying 7 digits For example, pi, number pi is 3.1415965 up to there. If you include more decimals, it will not take it. It's just round it up because it's using only 7 spaces to keep information about each real single precision variable. Any other question, people? Any other question?
Okay, doctor, thank you.
Okay, no problem. I'll try to see over the weekend if we could set meetings with each group, so we can be sure that every group is working. Okay, I'll try to do that tomorrow, because today, as I said before, it's a very complex day for me today. But tomorrow I'll try to publish a time schedule so we can meet with every group over the weekend. Probably, I don't know, probably Sunday morning, if possible. It's not going to be obligatory, but it's possible that somebody has questions. Okay, people, I'm late. See you. Bye-bye now.
Thank you, doctor.